Alright, so I want to get started talking about convergence, and at least for this video, a good reference is Weibull. I think chapter 5, I want to say. I don't know. Where they first introduced spectral sequences. And one of the challenges here, as I've said, is that, well, one of the challenges is many people use different notation, but even when it comes to convergence, people use lots of different terminology. And so I'm going to kind of pick and choose, and it will be a challenge as you go and look at other sources. Let me just warn you. So we'll just really get the tip of the iceberg this time, but I want to come back to that spectral sequence for a filtered space that we've been looking at and try to understand that actually it converges to the thing we claim. So in order to do that, we're going to need some terminology. So I'll do this for homology and cohomology, just so we've got really formally our definitions here. So homology spectral sequence, which is not the kind we were just looking at, is bounded if for each n, and I want this n to be my total degree, there are finitely many non-zero terms with that total degree. So maybe p plus q equals n. And I'm going to say on the E1 page, but let me say more in a moment. So really, once I have finitely many non-zero terms on the ER page, then that's also going to be true on the ER plus 1 page. So, I mean, if this is true for all degrees n, right? So that's really telling me that along the diagonals, I have these nice sort of finite supported kind of things, right? I've only got finitely many non-zero terms on each diagonal. And so when I take the differential and I take cohomology with respect to that, or homology, I guess, in this case, then certainly that's going to continue. So it really just needs to be true on some page that you know about, because then it will be true for all the other pages. But okay, in any case, let me remind you, for our homology setup, we've got our differential. I tried to do it backwards. It has by degree minus r, comma r minus 1. So as usual, total degree 1. And what that tells us is that for each PQ, I look at the PQ spot and there has to be some R naught such that that value stabilizes, in the sense that ERPQ is the same as ER plus 1 PQ for R greater than or equal to some R naught. Okay, so I look in the degree n part, and there are only finitely many things that I can hit in degree n minus 1. And so eventually I'm going to stop hitting things as I stretch further and further out along that diagonal. Okay, great. So this also tells me that if I look at Z infinity PQ, which I suppose I didn't define for the homology thing, but you can imagine we define analogously, that's just going to be ZRPQ for those R's. And the same with B infinity PQ. That'll stabilize. And so in particular, the thing that we're really after, our infinity page, which is the quotient of these, is actually just the rth page for some R. Well, okay, that's not really true for the whole page, right? This is just at some PQ spot, and what what R naught I need to stabilize at some PQ might be different for some other PQ. So I'm not saying that the spectral sequence collapsed and stopped, but at that particular spot, it will stabilize, and then this justifies that I can write E infinity PQ for that stable value. By the way, even saying the spectral sequence collapses, people have different terminology. So I say it collapses if at some point everything has stabilized, and sometimes people say, oh, it only collapses if in each total degree you only have one non-zero term. I don't know. Take your pick. Okay, so what's the point of all of this? Well, bounded is really going to be our best possible scenario. So if we have a bounded homology spectral sequence, I'm not trying to define bounded, we just did, but maybe let me emphasize it, that this is this very good case, that this converges, that's what I want to define, it converges to some homology groups if each Hn, so thinking of H star as the collection of all of the Hn, this has a finite filtration. And this is going to be important too. So we want to be in the nice bounded case with a finite filtration. Then we've got good convergence. So we've written this down before long ago, but this is I have some piece Fs Hn, and that's 0, and that sits inside a big chain. Okay, we've got Fp minus 1 Hn sits inside Fp Hn. I can't remember whether we call this ascending or descending. But the point is that this is a finite filtration, so we go between 0 and Hn in finitely many stages. Okay, well that's not quite enough, so I need it to be bounded. I need to have this finite filtration. Maybe let me even emphasize finite filtration. And I need to know something about my E infinity page. So it converges if there are isomorphisms E, P, Q, infinity with the filtration quotients. Oops. Oh, and I should have made that H. Oops. HP plus Q. That's, I want to be thinking about N as my total degree, as usual. So it makes it sort of annoying to write down. Okay, and in this situation is when we write things like we have a spectral sequence with E1, PQ, some term we know, and converging to the homology HP plus Q. Notice I'm not talking about the homology of a chain complex or a space or anything in particular right now. I'm just saying generally what does it mean for a bounded homology spectral sequence to converge. Okay, so I think this isn't really something new. I think we talked about this long ago. And we've said all along, right, when we cook up our E infinity page, what do we really mean? We just mean we're cooking up an associated graded for some filtration. And that's just what I'm making precise here. So here's our filtration, and here are our associated graded pieces, okay? Now let's write that down for the cohomology case. Try to be a little bit more brief, but I do think it's good to have this really explicit. So a cohomology spectral sequence is bounded. Well, essentially I want to say the same thing. So again, I'll say the E1 page, but it really doesn't matter. I just need some good place to start. If the E1 page has finitely many non-zero terms, in each total degree. Okay, and here in our cohomology setting, our dr has by degree r comma minus r plus 1, right? So again, total degree 1, the same story holds. In fact, you can always just take a homology spectral sequence and take p minus q, or sorry, p comma q, and replace it with minus p minus q and switch to a cohomology spectral sequence. Though it won't necessarily switch to the one you're thinking of, but it'll certainly switch the degrees of everything. Okay, so this has total degree 1, and this gives us that same sort of result. So at each spot, PQ, the value stabilizes. Okay, and that tells us that we have ERPQ is isomorphic to ER plus 1 PQ, and that's what we'll call EPQ infinity whenever R is greater than or equal to some R naught, where we've stabilized. And the spectral sequence converges. Well, this is a cohomological one, so we'll say converges to some cohomology. If, again, each H upper end now has a finite filtration, and people tend to write these the other way, so that finite filtration is going to look like FT HN on this side, and then all I mean is FP plus 1 is going to sit inside FP instead of the other way. Though, of course, it's all up to a choice of indexing. But I want this to stop at some finite stage at which I get all of HN. Okay? And, of course, I need to have these isomorphisms. That look like EPQ, whoops, I switched to homology, EPQ infinity, I should be able to identify with the filtration quotients. Okay, and the reason I wrote this out in its gory detail is I want to do just that. At least start to do just that in the case that we've been looking at. So now let's think about our filtered space. And I actually want to set this up just for the ease of this first description. Ultimately, I don't want to assume that my filtration has to be finite, but for now, I want to make it finite. So this is a filtered CW complex, probably not my CW filtration, but some nice cellular filtration. And wow, I think my handwriting is really deteriorating. Okay, so hopefully you can read this. So this is going to have some finite filtration, finite cellular filtration. Okay, and then of course we know what we're supposed to have is a first quadrant spectral sequence, and in fact we do at this point. We've justified that we have a spectral sequence that starts with E1PQ being HP plus Q of the filtration quotients. And what we haven't justified is this converging part to HP plus Q of X. Okay, so what do I need to do to say that this converges? Well, I need to identify a filtration of HP plus Q of X, and then I also need to find those isomorphisms with my E infinity terms, right? I really need exactly this piece here. Okay, so that's what we'll do now. And in order to do that, let me I don't want to draw the whole unraveled exact couple unless actually I might even just have it saved. Oh, look at that. Okay, might as well. So let's say that up here at the top at some finite stage, we've got hn of xn. Okay, so great, that was faster than I expected. Okay, so here, as usual, I'm going to take n to be p plus q. And let's remember how we constructed this spectral sequence when we were doing it the careful way. So we had our ZR PQ. These were x in HP plus q of xp, comma xp minus 1, such that we apply k and we can lift up the diagram r minus 1 times. So we were in the image of I to the r minus 1. Then we had our co-boundaries. So these looked like j of y in HP plus q, the same thing. Right, this was really a subset, probably subgroup even. One would hope. Okay, and then we have y in the kernel of I applied r minus 1 times. And we said that we had ZP Q infinity. This was the intersection of all these ZRs. Remember, they were nested. And that contained BPQ infinity because we had that nice nesting sequence. The Z's are all contained, and then inside that are all the B's. And so this was just the union of all the B's. Okay, and then our definition for this E infinity term is that we take ZPQ infinity and quotient by BPQ infinity. Okay, so what do we need to do? Well, as I said, we need to find a filtration of Hn of x, which is of course just Hp plus q of x. Okay, and we'll want some filtration, and then we want to identify the filtration quotients with this E infinity term. Okay, and if that's what we get, then we say the spectral sequence converges to that. Okay, and again, maybe let me just remind you, if we're in the nice bounded context, which we're hoping that we are, then we identify these EPQs with the filtration quotients, the E infinity terms, sorry, and then really that is actually the term on some page. So it's not like some opaque E infinity term that we never reach. Maybe we never reach all of those E infinity terms at once, but at any given spot we can stabilize. And in any given degree n, we can go far enough out that all of the things with that total degree have stabilized and so on. So this really is the best notion of convergence. Okay, so we want to see that we have that here. And so what we're going to do is filter the cohomology, and we'll make the pth filtered piece be, well, I want to make it the kernel of Hn of x mapping to Hn of xp. Of course, xp lives inside Hn of x, so I always have this map and then the other map on cohomology. And so that's really because my filtration is finite, and this is actually just Hn of x, this thing at the top, it really does map explicitly in this tower down. But in general, if I had something that's not a finite filtration, which ultimately we'll want to deal with, then I still have that map, I just don't maybe see it explicitly in this tower, right? But in this case, it's just going to look like composition of a bunch of these eyes. Okay, so we take the kernel of that map, and we'll filter in that way. So of course, if you're in the kernel of the map to xp plus 1, then you're in the kernel of the map down to xp. And so that's going to give us this filtration. So now we've got, 0. Maybe I should change up colors sometimes. Our last filtration will be Fn, right? Because there's only n places you can go down this tower. And that's just saying that you're in the, well, okay, what did that say? That said that you're in the kernel of the map from hn of x to hn of x. So that is definitely 0. Okay, good. Good sanity check. Then I've got fn minus 1, whatever that is. And so on. As I said, fp plus 1. hn lives inside fphn. And so on, all the way down to, well, what's the last thing? If I go all the way down to the very bottom, then I've got my x minus 1 living way down here. And that's just the empty set. So the cohomology is 0. So everything is in the kernel of that map, okay? And so that's all of hn of x. Okay, and in this case, you know, my hn, of course, really is hn of my space. But in general, it could be something else. In more general spectral sequences. I guess I should say what I'm trying to do is do the sort of smallest, easiest case that fits with the things that we've been doing, but ultimately we're going to want to look at more complicated situations. First of all, we'll want to let X not have a finite filtration, but then we'd want to consider things like we would see in the Serre spectral sequence, or the spectral sequence for a double complex, or the Bockstein spectral sequence, or even something maybe more complicated, ultimately the atom spectral sequence. So we'll need to generalize this quite a bit. But for now, in this nice finite case, yes, we do get a finite filtration of our hn of x. So that's good. And then that's not enough. We need to identify the E-infinity page. So the claim that I want to make, I just realized this video is getting pretty long, but I don't think it's worth stopping, so I'm going to push through. I apologize. This is going to be a long one. But the claim that I want to make is that we can identify the E-infinity page. This is going to be fp of hn mod fp plus 1. Yes, plus 1. The hn, I started thinking about time and got distracted. Okay, so we already know what those E-infinity terms are, right? They're the quotient of z infinity mod b infinity. But the hope is that we can identify them as these filtration quotients where those are coming from kernels of these maps. So just to write that out really explicitly, what is that fphn mod fp plus 1 hn that we're trying to find? Well, that's exactly the kernel of the map from hn of x to hn of x. I think I messed up my indexing. Yes, I apologize. I want to make this xp minus 1. Okay, that's just going to shift things off, and now I think I have a bunch of stuff to change. So, do I really get 0 when I do fn? Okay, I'm looking here. So, yeah, that's the kernel of hn of x to hn of x n minus 1. Okay, so no, that should be a plus 1. Just get rid of that. But I think when we get to, okay, I guess that means that really when we get down to 0 here. Okay, anyway, not a big deal, still a finite filtration, but my indexing was off from what I wanted to do. Let's hope that that still works out. Okay, and then I didn't finish writing this statement, right? That was just the first piece. Take that kernel, and then I want to quotient by the kernel from hn of x now to hn of x p. Okay, I just wanted to do that so it would exactly match up with the EPQ infinity that we've already defined. So let's keep going and see if that worked out as planned. Okay, in order to do that, in order to make this identification, I'm going to define something in between. And I'm really doing this because, again, I'm thinking about the infinite case, though that'll be a little bit more complicated, but sort of with a view towards that. I'm going to define hn of xp sub infinity. Okay, so this is going to be a new thing. And what is this? This is x in hn of xp. So notice this isn't something in the spectral sequence, right? Our spectral sequence only has the filtration quotients. It goes through all this other stuff, but all that stuff is not in the spectral sequence. Okay, but now I'm looking at something over here in hn of one of these pieces, xp, and we'll find out if that's really what I meant or if I meant p minus 1 or something. Okay, let's hope this works out. So I don't want to just take all of those things. I want to take those things that lift all the way up to hn of x. And now with a view towards thinking about this for the not finite case, I might want to take something that lifts to the inverse limit or something that lifts all the way up the tower, which is not exactly the same. And so we'll have to come back and deal with those subtleties. But all I mean to say is that this definition that I should take here is a little bit more complicated if my filtration's not finite. Okay, but now what do I want to do? I want to notice that K induces a map from the cocycles ZPQ infinity. I claim it surjects onto this hn of xp infinity. Okay, and this will partly tell us if our indices are right. So what is our ZPQ infinity? That's the intersection of all the ZR, and ZR are the things, well, you take the thing and you apply K, and then you can lift up the diagram R minus 1 times. Okay, so those are the things that I take this little x, I apply K, and then I can lift up the diagram R minus 1 times. Well, if I take the ZPQ infinity, that means that I can just keep lifting forever, right? So, okay, the things that are in hn of xp that I can lift all the way up the diagram to hn of x, those are exactly surjected on by k. Okay, because of our definition of ZPQR and even ZPQ infinity. Okay, let's think about the kernel of that map. This is also why I keep the video shorter, because my voice starts to go eventually. Okay, so what is the kernel of that map? Well, the kernel of that map is anything that I had here that I could send K over and lift all the way up the diagram, and I sent it over and I got 0. Okay, well, if I sent it over and I got 0, then by exactness, it came from something, from J of something, right? And so that kernel is precisely the image of J. And the image of J, I claim, is in fact this BPQ infinity. So let's think about that. Well, BPQR are things that look like J of Y here, where that Y was in the kernel of going down. Okay, so BPQ infinity means that it's in the kernel going all the way down. Well, yeah, everything, eventually you go down and you hit 0, right? Because this is that filtration of x, and my x minus 1 is 0. So of course, everything is going to eventually go to 0 if I'm looking at, oh, I think I said something funny. I'm trying to say that everything that's in the image of J will eventually go, sorry. The J maps those things isomorphically here. Okay. Okay. I think I stand by that statement. So if I take anything here and look at J mapping to it, well, anything here is going to go to 0. Okay, so I think because that B involved J of Y, it really was the things over here after I fit them with J, then yes, this statement is true. Okay, let me write it down. I really get tripped up in all of the indices here, and it makes it hard to say the right words. And of course, you all aren't here with me to say, no, Clover, that does not quite make sense. I think you mean this. So, okay, hopefully I've caught myself. What I'm trying to say is the kernel here is BPQ infinity, and that's really because that's the image of J. So remember, we applied K to do this map. Really, it was just K restricted to these cocycles. And so we applied K, and if we get 0, that means that thing came from the image of J. Okay, so those things are precisely BPQ infinity. Okay, great. All of that is to say, at long last, that EPQ infinity which of course by definition was ZPQ infinity mod BPQ infinity. Well, this map was surjective and we just figured out its kernel, and so this is isomorphic to this thing we called Hn of xp infinity. And remember that Hn of xp infinity, that's just the things in Hn of xp that lift all the way up to Hn of x. Okay, so now let's think about what these filtration quotients look like. FPHN mod FP plus 1 HN. Okay, so I'm supposed to look at things that are in the kernel of Hn of x mapping to Hn of xp minus 1, but not in the kernel where I kill the things that are in the kernel of going one further. Okay, so I'm just going to draw a little piece of this sequence again. So I've got my Hn of x way here at the top, and then I get down to Hn of xp, and then Hn of xp minus 1. And here's my k coming in, and this is I, and the whole point is that if you are in the kernel of this map, but not in the kernel of this map, then you mapped to something non-zero, and then I killed you, right? But now this is part of a long exact sequence. So by exactness, if you had some non-zero class here, then it went to 0, then it came from something back here. But that map K is precisely how we identify this with our E infinity term. Okay, so we're exact at this spot, and that tells us that FPHN mod FP plus 1 HN, this really is Hn of xp infinity. Okay, I think I maybe said that a little bit strangely, so let me just say again. Okay, so if I'm in the kernel going all the way down but not part way down, Well, then I've got some class here that's non-zero that got sent to 0. And the kernel of I is exactly the image of k. But k is surjective here, right? The image of k on just the infinite cocycles is hn of xp infinity. And moreover, that map identifies this as isomorphic to hn of xp infinity. So now we've got that this is exactly EPQ infinity. Okay, I think it's getting late, and hopefully that made sense. What is the moral of this story? The moral is that yes, we do have a spectral sequence for a filtered space, and we've already seen how to cook that up. We had a heuristic, kind of here's how you should think about it, but now we've made it really precise. We definitely have a spectral sequence where the rth page is the homology of the r-1th page, where we use that d r-1 differential. And now we can say that indeed this spectral sequence converges to an associated graded for a filtration of the thing that it was supposed to converge to, the homology of our space. Okay, so our EPQ infinity terms, we just identified them with the associated graded filtration quotients for that filtration of HN. And what was that filtration? Remember that we used the kernel of this map. Okay, so it really did come from something kind of meaningful coming from spaces. That filtering of the spaces gave us a filtering of this algebraic object, the cohomology, and it's that leads us to being able to identify the E infinity terms with those filtration quotients. Okay, so this is the best possible case where we've got a bounded cohomology spectral sequence, we've got a finite filtration, and we've identified those EPQ infinity terms with their filtration quotients, and so the spectral sequence converges in this case. Now again, of course, we want to be able to do this when our filtration of the space is not finite. We should still have the same result. We want to be able to deal with even more complicated situations. What if our spectral sequence isn't bounded? Can we still say something about convergence? So we'll investigate those next.